Welcome! Today, we'll be tackling problem number 1492, the kth factor of n. This is an interesting problem that tests your understanding of factors and efficient iteration techniques. Stick around as we explore various approaches, analyze their complexities, and derive an optimal solution. Let's dive in. The problem we're solving is called the kth factor of n. Here, you are given two positive integers, n and k. A factor of an integer n is any integer I such that I is greater than or equal to 1, less than or equal to n, and n is divisible by I without leaving a remainder. Your task is to find the kth factor of n when all the factors of n are listed in ascending order. If n has fewer than k factors, your function should return -1. For the input format, you'll always receive two positive integers, n, which ranges from 1 to 1000, and k, which also ranges from 1 to 1000. The output will be a single integer, either the kth factor of n or -1 if there are not enough factors. Let's look at some examples to clarify. In the first example, the input is n equals 12 and k equals 3. The factors of 12, listed in ascending order, are 1, 2, 3, 4, 6, 12. Here, the third factor in this list is 3, so the output is 3. In the second example, the input is n equals 7 and k equals 2. The factors of 7 are 1, 7, since 7 is a prime number. The second factor in this list is 7, so the output is 7. In the third example, the input is n equals 4 and k equals 4. The factors of 4, in ascending order, are 1, 2, 4. However, there are only 3 factors, so the fourth factor does not exist. As a result, the output is -1. The constraints for this problem are as follows: n and k are both between 1 and 1000, inclusive. Additionally, it's important to handle cases where k is greater than the total number of factors of n. For instance, if n equals 10 and k equals 5, you would return -1 because there are only 4 factors of 10. Now, consider a few additional edge cases. If n is a prime number, it will always have exactly 2 factors, 1 and n. For example, if n equals 13 and k equals 3, the output should be -1 because there are only 2 factors. Also, if k equals 1, the result will always be 1, since 1 is a factor of every positive number. Finally, for large values of n and k, your solution needs to be efficient. For instance, if n equals 1000 and k equals 10, your approach should compute the first 10 factors without unnecessarily evaluating all factors of 1000. These considerations will help ensure your solution is both correct and optimized. To begin, let's consider the brute force approach. The intuition here is simple. If we want to find the kth factor of a number n, we can iterate through all integers from 1 to n, checking each one to see if it divides n evenly. If it does, we count it as a factor. Once we've counted up to k factors, we return the current integer as the kth factor. To break this down into steps, first, start with a count of 0. Then, iterate through all integers I from 1 to n. For each I, if n modulo I equals 0, increment the count. If the count reaches k, return I as the kth factor. However, if the loop ends and we haven't found that many factors, we simply return -1. This approach is straightforward and easy to implement, but it has a time complexity of O, n, as we're iterating through all integers up to n. On the bright side, it has a space complexity of O, 1, since no extra memory is used. Now, while the brute force approach is intuitive, it has its downsides. Specifically, it becomes inefficient for large values of n, given its O, n, time complexity. To address this, we can turn to an optimized approach that limits the search space. The key insight here is that factors of a number come in pairs. For example, if I is a factor of n, then n divided by I is also a factor. This means we only need to iterate through integers up to the square root of n, as any factor larger than the square root will already have been accounted for as part of a pair. The steps for this approach are as follows: iterate through integers from 1 to the square root of n. If n modulo I equals 0, then both I and n divided by I are factors. As we go, we can either maintain a sorted list of factors or simply count them. Finally, we return the kth factor from the list, or -1 if there are fewer than k factors. This reduces the time complexity to O, sqrt, n, which is a significant improvement over the brute force method. Depending on whether we store factors, the space complexity can range from O1 to OK. This optimized approach offers clear advantages over the brute force method, particularly for large values of n. By leveraging the fact that factors come in pairs, we substantially reduce the number of iterations. However, care must be taken to correctly handle these pairs to ensure the factors remain in sorted order, especially when n is a perfect square. As an alternative, we could consider a more advanced strategy, binary search on the count of factors. The idea here is to narrow down the range of potential factors more efficiently. However, this method is complex and less practical for this particular problem, given the constraints and the relatively simpler solutions already available. While it's an interesting theoretical approach, its added complexity makes it less appealing in most cases. The optimized approach of iterating up to the square root of n stands out as the most practical strategy for solving this problem. It strikes the right balance between efficiency and simplicity, reducing the number of iterations without introducing unnecessary complexity. The key insight that factors come in pairs allows us to limit our search space, and maintaining the correct order of factors is straightforward since one factor in each pair is always less than the square root of n compared to the brute force approach. This method is significantly faster, especially for larger values of n. Moreover, it avoids the memory overhead of storing all factors unless k is large, making it efficient in terms of space as well. While the binary search approach is faster in theory, it is harder to implement and not necessary given the problem's constraints. Thus, the optimized approach is both practical and effective, making it the ideal choice for finding the kth factor of n. To begin, the problem asks us to find the kth factor of a given integer n. Simply put, a factor of n is any integer that divides n without leaving a remainder. The goal is to determine the kth smallest factor of n in ascending order. The brute force approach to solve this problem is straightforward: iterate through all integers from 1 to n, check which ones divide n without a remainder, and count these valid factors. When the count reaches k, we return the current number as the kth factor. First, we initialize a counter called count to 0 to keep track of how many factors we've found so far. Then, we loop through every integer I from 1 to n. At each step, we check if n% I == 0. If it is, we increment the count by 1 since I is a factor. After incrementing, we check if the count matches k. If it does, we return I immediately as the result because we've found the kth factor of n. Now, there's an additional condition we need to handle. What if we loop through all integers up to n and still don't find k factors? In this case, the algorithm concludes that the kth factor does not exist, so we return -1. Let's walk through some examples to understand this approach better. Take n = 12 and k = 3 as the input. Starting with count = 0, we iterate over integers from 1 to 12. At I = 1, 12% 1 = 0, so we increment count to 1. At I = 2, 12% 2 = 0, so count becomes 2. At I = 3, 12% 3 = 0, and count reaches 3, which matches k. Thus, the output is 3, the third factor of 12. Another example, for n = 7 and k = 2, we start iterating with count = 0. At I = 1, 7% 1 = 0, so count becomes 1. At I = 7, 7% 7 = 0, and count reaches 2, matching k. Therefore, the output is 7, the second factor of 7. Let's consider one more example to handle edge cases. If n = 5 and k = 3, we start with count = 0 and iterate from I = 1 to 5. At I = 1, 5% 1 = 0, so count becomes 1. At I = 5, 5% 5 = 0, so count becomes 2. However, the loop completes without count ever reaching k = 3. In this case, we return -1 since the third factor does not exist. From these examples, we can extract several key insights. First, the divisibility check n% I = 0 is fundamental to identifying factors and runs in constant time. However, iterating from 1 to n gives the brute force approach a time complexity of O(n), which can be inefficient for large values of n. On the positive side, the algorithm terminates early once the kth factor is found, which can save time in some cases. Finally, it handles edge cases gracefully, such as when k exceeds the total number of factors or when n is very small. In terms of data structures, the algorithm is minimalistic. It uses a simple integer variable count to track the number of factors found so far. No additional data structures are required, which keeps the space complexity at O(1). For complexity analysis, the time complexity is O(n), because we iterate through all integers from 1 to n. Since no extra space is used, the space complexity remains O(1). However, there are optimization opportunities to improve efficiency. One key idea is to iterate only up to the square root of n. Factors of a number occur in pairs, such as 1, 12, 2, 6, 3, 4, for n equals 12. By iterating only up to sqrt n, and tracking both factors in each pair, we can reduce the time complexity to O sqrt n. Another optimization is to store all factors in a list and sort them. This allows direct access to the kth factor, which is helpful when k is large but n is small. The pseudocode for the brute force approach is straightforward: initialize count to 0, loop through 1 to n, check divisibility, and increment count until the kth factor is found. If the loop completes without finding the kth factor, return -1. Now, let's look at the optimized approach that iterates up to the square root of n. Here, we maintain a list called factors to store all divisors of n. For each integer I from 1 to sqrt n, if n%i equals 0, we add I to the list. Additionally, if I is not equal to n//i, we add n//i to capture the paired factor. After collecting all factors, we sort the list. Finally, we return the kth factor if k is within bounds, otherwise, we return -1. This method is much more efficient for large values of n because it processes only up to sqrt n, and leverages factor pairs to minimize computations. This Python implementation solves LeetCode problem number 1492, the kth factor of n using a brute force approach. The problem requires finding the kth factor of a given integer n. If there are fewer than k factors, the function should return -1. The code begins by defining the kth factor function within a solution class. The function takes two inputs, n, the integer whose factors are to be examined, and k, the index of the factor to find. A variable count is initialized to 0 to keep track of the number of factors encountered during iteration. Next, a for loop iterates through all integers from 1 to n. The if statement checks whether the current number I is a factor of n by evaluating n%i equals 0. If the condition is true, the counter count is increment by 1. The second if statement checks whether the current factor is the kth factor by comparing count to k. If count equals k, the function immediately returns the current factor I. If the loop completes without finding k factors, the function returns -1, indicating that there are fewer than k factors for the given n. This approach has a time complexity of O(n), because it examines all integers from 1 to n. While this is not the most optimized method, it is straightforward and satisfies the problem's requirements for small to moderate values of n. The edge case where k exceeds the total number of factors is handled gracefully by returning -1 after the loop concludes. This is the Java implementation of LeetCode problem number 1492, the kth factor of n. The logic mirrors the Python solution, iterating through all integers from 1 to n to find factors of n. The method uses a counter to track the number of factors and returns the kth factor when found. If fewer than k factors exist, it returns -1. Key differences include Java's explicit type declarations and the use of a for loop with a bounded range. In this example, we are tasked with finding the third factor of the number 12. A factor is any integer that divides the number without leaving a remainder. We start by initializing a variable count to 0, which will help us keep track of how many factors we encounter as we iterate. Next, we systematically check each number from 1 to 12 to see if it divides 12 evenly. First, we check 1, and since 12 divided by 1 leaves no remainder, we increment count to 1. This makes 1 the first factor. Then we move to 2, which also divides 12 evenly, so we increment count to 2, identifying 2 as the second factor. Next, we check 3, and again it divides 12 without a remainder, so we increment count to 3. At this point, since count equals k, which is 3, we immediately return 3 as the third factor of 12. Now, let's look at the next example where we need to find the second factor of 7. Since factors are integers that divide the number without leaving a remainder, we begin by initializing count to 0 to track the factors we find. Starting our iteration from 1 to 7, we first check if 1 divides 7 evenly. It does, so we increment count to 1, making 1 the first factor. Next, we check numbers 2 through 6, but none of these divide 7 evenly. Finally, we arrive at 7, which divides itself without a remainder, so we increment count to 2. Since count now equals k, which is 2, we return 7 as the second factor of 7. In this example, we are asked to find the fifth factor of 15. To solve this, we initialize count to 0 and begin checking each number from 1 to 15 to see if it divides 15 without leaving a remainder. First, we check 1, which is a factor, so we increment count to 1. Next, we test 2, which does not divide 15 evenly, so we skip it. Then, we check 3, which is a factor, so count becomes 2. Moving on, 4 doesn't divide 15 evenly, so we skip it. Checking 5, we find it is a factor, so count becomes 3. We continue checking numbers 6 through 14, none of which divide 15 evenly. Finally, we check 15, which is a factor, so count becomes 4. However, since we reach the end of the loop and count is still less than k, which is 5, we conclude that the fifth factor does not exist and return -1. The final output for the previous example confirms that the fifth factor of 15 does not exist, so the answer is -1. Now, let's summarize the key observations from the solution. This approach works by iterating from 1 to n and checking if each number divides n evenly. The variable count keeps track of the number of factors found, and as soon as count matches k, we return the current factor. If the loop ends without finding k factors, we return -1. The time complexity of this solution is O(n), because we iterate through all numbers up to n. For edge cases, if k is greater than the total number of factors, the solution correctly returns -1. When k is 1, the output is always 1, as 1 is a factor of every number. For prime numbers, the second factor will be the number itself, and if k exceeds 2, the function will return -1. To analyze the time complexity of this solution, we start by observing that the algorithm iterates through all integers from 1 to n to determine if each integer is a factor of n. The outer for loop runs from I equals 1 to I equals n, which means it can execute up to n iterations in the worst case. This contributes an O(n) complexity just from the loop itself. Within each iteration, the algorithm performs a modulo operation, checking if n% I equals 0 to determine if the current I is a factor. Since this modulo operation is a constant time operation, O(1), it does not add to the overall complexity but is executed n times in total. Additionally, when a valid factor is found, the algorithm increments the count variable and checks if the kth factor has been reached. These operations are also O(1) and executed conditionally. Therefore, the overall time complexity is dictated by the number of iterations, leading to O(n). While it's true that the loop may terminate early in cases where the kth factor is found quickly, such as when k equals 1 or 2, big O notation focuses on the worst-case scenario, which remains O(n). Now let's consider the space complexity of the solution. The algorithm uses a constant amount of extra space, as it only relies on a few integer variables, count, I, and k. These variables do not scale with the input size, meaning the memory usage remains fixed regardless of how large n becomes. Importantly, no additional data structures such as arrays or lists are used, and the solution does not involve recursion, which would introduce stack space overhead. Because of this, the auxiliary space required by the algorithm is O(1). In summary, the space complexity of the solution is constant, or O(1), as the memory requirements do not grow with the input size. When comparing this brute force approach to potential optimizations, it's clear that the current solution checks all integers from 1 to n, resulting in an O(n) time complexity. However, a more efficient approach could involve iterating only up to the square root of n. This optimization takes advantage of the fact that factors of a number come in pairs, such as I and n/i. By limiting the iterations to the square root of n, the time complexity could be reduced to O(n). Additionally, it's worth noting the distinction between the best case and worst case scenarios. In the best case, the kth factor is found early, allowing the loop to terminate prematurely and reducing the number of iterations. However, big O analysis focuses on the worst case, where k is large or even exceeds the total number of factors, which results in O(n) time complexity. Finally, the mathematical reasoning behind this complexity is straightforward. The loop executes up to n iterations, with each iteration involving constant time operations like modulo, increment, and comparison. Thus, the total time complexity is O(n)(O)(1), which simplifies to O(n). Meanwhile, the space complexity remains O(1), as no additional memory is allocated dynamically, nor are recursive calls involved in the process. When solving the problem of finding the kth factor of n, there are some common mistakes you should be aware of. First, not checking all factors is a frequent issue. Many people iterate only up to n/2 or sqrt n, and forget to include the paired factors, such as n divided by the current divisor. Remember, while iterating up to sqrt n is efficient, you must also consider these paired factors to ensure none are missed. Another mistake involves off-by-1 errors when counting factors. This happens when you start counting from 0 instead of 1, which is problematic because the problem assumes 1-based indexing. Miscounting in this way leads to incorrect results. Finally, ignoring larger values of n is a critical error. If you assume n is small and use an O(n) approach, it will work for small inputs, but for larger values, such as n greater than 10 to the power of 6, the brute force method becomes too slow and can result in time limit exceeded errors. These are all important issues to avoid in your implementation. Another common area where mistakes happen is in handling edge cases. For example, if k is greater than the total number of factors or if n is a prime number, your solution might fail if these scenarios aren't properly accounted for. Not handling these edge cases can lead to incorrect outputs or even runtime errors. Inefficient sorting of factors is another mistake that can slow down your solution. Some approaches collect all factors and then sort them to find the kth factor. However, sorting introduces unnecessary overhead, with a time complexity of O(n) log n. This can be avoided by directly counting factors in order as you iterate, making your solution both cleaner and faster. By addressing these issues, you can ensure your solution is robust and efficient. When preparing for interviews, efficiency matters. While brute force approaches may be acceptable for small inputs, interviewers often expect optimized solutions. For example, iterating up to sqrt n and leveraging the symmetry of factor pairs, such as I and n divided by I, can significantly reduce the computational load. Understanding factorization is key here. Recognizing that factors always come in pairs allows you to focus on a smaller range of numbers. It's also important to handle edge cases effectively. Be sure to clarify constraints, such as the range of n and k, and consider scenarios like k being greater than the total number of factors or n being 1. Additionally, when presenting your solution, communicate trade-offs. Explain the differences between approaches in terms of time complexity, space complexity, and readability. Finally, exploring related problems like happy number, ugly number, or count primes can deepen your understanding of factorization patterns and help you connect ideas across different challenges. There are several approaches to solving this problem, each with its own trade-offs. The brute force method involves iterating through all integers from 1 to n and counting factors. While this approach is simple and easy to implement, it's inefficient for large values of n due to its O(n) time complexity. A more optimized iteration method involves iterating up to sqrt n and considering paired factors. This reduces the range of iteration, making it much more efficient, with a complexity of sqrt n. However, you need to handle duplicates carefully, especially for perfect squares. Another option is pre-computing factors for all numbers up to a certain limit. This is useful when you need to handle multiple queries, but it comes with a higher space requirement, specifically O(n) sqrt n. Lastly, using binary search on sorted factors is another alternative. While this approach is useful in some scenarios, generating and sorting the factors introduces additional overhead, which may not always result in better performance. Choosing the right approach depends on the problem constraints and the trade-offs you're willing to make. Great job! To recap, we discussed how to efficiently determine the kth factor of a number by leveraging mathematical properties and optimizing our iteration process. Remember, understanding the fundamentals of factorization can help in many similar problems. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!